So today we're going to start a new chapter, but there's just a small little topic that was left from the previous class that I want to cover now. And it had to do with using our hydrostatic equation in a situation where there is rigid body motion, so the whole mass of liquid is moving at a certain acceleration. And we saw at the end of last lecture that if there was some linear acceleration, like when you're carrying a cup of coffee and you suddenly hit the brakes in your car, and the whole surface of that liquid will become inclined. And we calculated what that slope was going to be depending on the acceleration. So you're used to that from your everyday experience, but the other situation happens when you have uniform rotation. So we're going to consider now, so I've placed there the equation that we were dealing with at the end of last class. We wrote it in this form, and it's the same as the hydrostatic equation, except in the hydrostatic case, we would have on the right-hand side equal to 0 because there is no acceleration. But in this case, there is acceleration, so the contribution of the pressure gradient and the contribution of the hydrostatic column of liquid must equal the acceleration, the contribution of the acceleration, some rigid body, uniform acceleration. So let's consider the case of, say, a container which is rotating with a constant angular velocity in this case. So we can look at the acceleration of a small fluid element which is indicated in this sketch. This is supposed to be a small fluid element, okay, here in this picture, and this is some sort of liquid inside a container. So there is, of course, a given radius r indicated here, an acceleration which is directed toward the axis. It's the centripetal acceleration, right? And we know how to calculate from basic physics that acceleration, the centripetal acceleration, is r omega squared, where omega is our angular velocity, and it's directed toward the axis. So to look at this problem, because of the symmetry that we have here, we are going to want to write this divergence operator in cylindrical coordinates. So how does that gradient operator look like in cylindrical coordinates? That is r, theta, and z in the vertical direction. The gradient operator will be this little e is going to be our unit vector. So unit vector in the r direction times the partial derivative with respect to r, plus the unit vector in the theta direction times, oh sorry, this is a 1 over r here, 1 over r d theta, and then e, the unit vector in the z direction multiplied by the partial derivative with respect to z. So that's our gradient operator, where here basically in the previous equation we had written k. This is the same that I'm writing now as e in the z direction, the unit vector in the z direction. So let's look at the acceleration. The acceleration in the radial direction, we have it right here. The acceleration in the other two directions is going to be 0. So acceleration in the theta direction is 0, and the acceleration in the z direction is 0. So now we can write the above equation. We're going to write this equation component-wise. The only interesting one is, of course, this one in the r direction. dp dr is equal to this guy here, but multiplied by rho. Rho times the acceleration. Rho r omega squared. That's rho times a, just in the r direction. The other guys, so this one is 0, but of course in the vertical direction we also have the weight. Weight in the vertical direction, nothing in the angular direction, and just centripetal acceleration in the radial direction. Make sense? We have the three components. dp dr, theta equals 0, and dp dz equal minus gamma. So this is the one we're used to. We know about this one. This is just the hydrostatic relation. In the angular direction, there's nothing interesting happening, but here we have the centripetal acceleration and the pressure gradient in the r direction. So there's a pressure gradient there. There's a differential of pressure. So let's look now at what we would like to see, what would be an expression for a constant pressure, because that will give us an idea of how the surface looks like. The surface of the liquid is a surface of constant pressure because the whole surface is at atmospheric pressure. So what does a surface of constant pressure look like? So let's look at the differential of pressure. And this from our calculus of several variables. We know that dp is going to be equal to dp dr times dr plus dp dz times dz. We already can ignore the theta angle, it's not necessary. So now we can see what we can use the above expressions and write dp is equal to rho, this guy here, rho r omega squared times dr minus gamma times dz. Just using these two equations that we just obtained for the component-wise acceleration. So now we can look at this a little bit more. Notice that on a horizontal plane, for example, if dz equal to 0, we get dp is equal to something which is greater than 0 because it's omega squared is positive, rho is positive, r is positive. So if dz was equal to 0, we get dp equals something positive. So there is a gradient of pressure different than 0 on any line which is a horizontal line. Any horizontal line, oops, that's very crooked, let's try again. The problem is that I only can write in white rather than properly erased with my tools. So this would be a line of dz equal to 0, right? And in this line of dz equal to 0, we will have a non-zero pressure gradient. There is a pressure gradient. So that is interesting. Now the next, what we find is then that the pressure, basically the pressure increases with radius, right? As the radius gets larger, from 0 to the edge of the container, the pressure increases. So it's like a hydrostatic situation, but instead of the hydrostatic relationship with depth, we have here a similar relation with respect to the radius. As we go from the center to the edge of the container, there is increasing pressure. It's like going deeper in a pool instead you're going outwards in the rotating container. Make sense? Yes? Good. So now we want to find what shape does this surface here have. The shape of this surface, okay? To look at that, we have to find what shape is obtained from dp equal to 0. To do that, I'm going to have to clear a little bit the slides here. I don't want to erase everything, so I'm just going to use my fancy eraser here to make a little space in this same slide so that I don't have to erase everything. We have up to here. We're good up to here. Okay, so dp equal to 0 is going to give me a surface of constant pressure. You agree with that? Make sense? Yes? Okay. So dp equal to 0 means this guy over here equal to 0. So I can write rho r omega squared dr equal to gamma dz from here, making that equal to 0. And now I can rearrange this thing and integrate. So I can write dz dr, just separating over, rearranging a little bit, rho r omega squared divided by gamma, which is, I have rho divided by gamma here, so I could just put g at the bottom. It would be the same thing. So now I can integrate with respect to z, and this is with respect to, with respect to r, and I have an r here, so when I integrate I get r squared half, right? Integrate with respect to r, down here, I get r squared half. Let me change pen so that it's more clear, and I can write z is equal to omega squared r squared divided by 2g plus a constant of integration. So simply this tells us that there is a parabolic shape on the surface. The surface of the liquid adopts a parabolic shape when we have a uniform angular acceleration in a container of liquid. So you remember that the centripetal acceleration is r omega squared, and the equation I have says that I have this vector equation, right? In this vector equation, I separate into 3 components. In the radial direction, I only have the radial component of the divergence and rho times the radial acceleration. This guy only exists in the vertical direction, so I don't have to worry about this term when I'm looking at the radial direction. I have only dp dr and rho times the acceleration in the radial direction, so I multiply this guy by rho and I get that first component. So I'm taking this one component-wise. In the theta direction, the acceleration is 0, this guy over here with gamma is also 0, and I have dp theta equal to 0. That term is clear. The third component is the component in the vertical acceleration. In the vertical acceleration, I have no acceleration in the vertical component, but I have the weight component, gamma k. Gamma is zeta the same. Any more questions? I want to make sure you have followed this example. Okay, if that's the case, then let me just show you an application of this. So, a liquid mirror telescope, or abbreviated LMT, is a telescope. So, a telescope mirror in general has to have a parabolic shape. Okay, but to build these things out of glass, it's very expensive, very difficult. And so one can have a liquid mirror telescope, which is basically some layer of reflective liquid, such as mercury. Mercury would be a little, perhaps, well, you can use it, but it's a little bit, you have to be careful because it's toxic. But imagine we had a pool, a layer of mercury, and we put it on a rotating table and impart some uniform angular acceleration. The shape, the surface is going to adapt this parabolic surface. Excuse me. Back in business, okay. So the liquid layer of, say, mercury will adopt a parabolic shape, and this is used to as a telescope to observe the sky. Now, the only disadvantages of this are that it can only actually look upwards in the sky. If you had a glass shape, you can point it in any direction. But this solution is cheap. You don't have to really do that precision fabrication of the parabolic glass, but you can only look up in one direction in the sky. However, there are a lot of telescopes like this. It's a very cost-efficient solution if you're in a good location and there's something interesting right above you in the sky that you want to see with the telescope. So, here's an application. That was the last bit that I had for the chapter on statics. So now we're going to start this new chapter on fluid dynamics. By fluid dynamics, the basics of fluid dynamics are these relations: conservation of mass, conservation of momentum, conservation of energy, and the Bernoulli equation is a sort of a subset of it can be derived in many ways. We will discuss how one can obtain. It can be seen as either conservation of momentum or conservation of energy, but I put it in a separate class onto itself because it's probably the most used equation in fluid dynamics, and perhaps also the most abused. So we will discuss how not to abuse Bernoulli's equations. So this whole chapter really rests on these principles, basic principles of physics. Mass is conserved. Well, we don't consider any nuclear reactions, okay? So that possibility of conversion of mass into energy through E equals mc squared. Forget about that. We don't consider any nuclear reactions, and so with that assumption, mass is always conserved. It's not created nor destroyed. Momentum is conserved and energy is conserved. That's going to be the basic principles for this whole section of the lectures. So what do we mean by conservation of mass? Basically, if you have a tank with one inlet, one outlet, very simple, while the tank is filling and no mass is going out, there will be an increase of mass inside the tank. Natural. You understand that? Once the whole thing is filled up, the mass that comes in has to equal the mass that goes out. Simple as that. So, how do we use this in engineering? How do we use the conservation of mass? First, we draw a control volume, we call it a control volume, around, say, this tank, and enclosing the tank. And so we know that while the tank is filling, there will be no outflow, there's only inflow, and the mass inside this control volume is going to be changing. So here's a control volume, and the mass is changing while there's no outflow. once the outflow starts, we need to consider both change of mass inside the tank and inflow-outflow. And once the tank is full, the mass doesn't change anymore inside the tank. So this also introduces to us the concepts of steady and unsteady flow. So basically, the whole concept here is that the change of mass inside this control volume has to be equal to the difference between the mass coming in and the mass going out. In the beginning, while the tank is filling, no mass is going out, so there's only mass coming in, and therefore there's a change of mass inside the volume. Once the tank is full, the mass coming in equals the mass going out, and the mass inside the volume doesn't change anymore. Very straightforward physical concept that I'm sure you are familiar with. But let's introduce the concept of steady and unsteady flow. So while the tank is filling up, the mass in the control volume that we've drawn here in red changes, right, in time. So there is this dt is different than zero. dt of the mass in the control volume is different than zero. This is an unsteady situation. So there's some mass which is accumulating in this case because there's mass coming in, no mass going on, so mass is accumulated inside the tank, and so we have a ddt of mass different than zero, and this is the flow is unsteady. Now, once the tank is full, then the rate at which the mass enters has to be equal to the rate at which the mass exits. And therefore, mass cannot be created or destroyed. Mass here, then we have ddt in this case of the mass is going to be equal to zero, and the flow is steady. So basically, the definition of steady flow is simply that the derivative of mass, in this case, in really any derivative with respect to time is equal to zero. If the derivatives with respect to time are zero, the situation, the system is steady. So let's look at the simplest case of applying the conservation of mass in an engineering situation, which is when you have steady one-dimensional flow. Steady means, already we said, steady means that all the partial derivatives with respect to time are equal to zero. In particular, the derivative of mass with respect to time is equal to zero. And one-dimensional, by one-dimensional, basically, we mean that we assume that there is a uniform velocity profile in the cross area. And so this simplifies things quite a bit. But a lot of engineering systems are like that, or we can assume some sort of average velocity in the cross-sectional area, and so we can, simplify our lives quite a bit by assuming that this is a one-dimensional flow. So the mass flow rate or m dot is equal to, in this case, the density times the change of volume, and the change of volume is going to be the area times how much volume. So in this picture here, we have a volume that enters some sort of control volume here, and then exits the control volume, and the distance that is covered by that liquid is V times delta T. And if I multiply by area, that's a change in volume. If I multiply by density, it's a change in mass. So rho times A times V is our mass flow rate. So for steady flow, we have that dm dt is equal to 0, which indicates that in this situation that we have depicted in this simple animation, we should have that rho 1 A1 V1 has to be equal to rho 2 A2 V2. Normally the density is constant, and so it's going to be cancelled out from that equation, but just in general, let's leave it as rho 1 and rho 2, just in case. In case the fluid was compressible, if it was a gas, there might be a change. So in this situation, again, steady and one-dimensional, the other trick that we should remember is that mass flows are additive. What do I mean by that? That if, for example, a duct, like is drawn there, were to split in two, like that, then the mass going in has to equal the mass going out as before, so there's no change in that basic concept. And so if the duct splits, the total outflux must be equal to the total inflow, and we would have here, like is shown in the animation, that rho 1 A1 V1 has to be equal to rho 2 A2 V2 plus rho 3 A3 V3. Or if we have multiple outlets and inlets in a system, we could simply write that the sum of rho I AI VI is equal to 0. That is for steady one-dimensional flow, so we're assuming that the velocity is uniform in the cross-section. Many times we can assume that, we can use an average velocity, and that works. Occasionally we won't have that. We could have a general situation where really the velocity changes in the cross area. For example, we could have a parabolic flow. Say the velocity here, for example, adopts a parabolic profile, and we want to use that profile in our calculation. Then we use this general equation where the mass flow rate is equal to the integral of rho v dA. So for example, if we had a parabolic profile, inside a pipe, parabolic velocity profile, suppose that the velocity with respect to r was equal to a maximum velocity times 1 minus r divided by big R, which is the radius of the pipe, squared. That's our parabolic velocity profile. To be able to obtain an expression now, we have to be able to write this dA as a function of r. So we can write for a pipe, we can take sort of like a ring-shaped bit of area and integrate from r equal to 0 to the radius of the pipe. So this is the pipe cross-section I'm drawing. And so I can write that a differential of area is equal to 2 pi r times dr. And I can now find an expression by putting this ring element into my dr. I could find m dot is equal to 2 pi. We have rho, we have v max. All of these things are constant, and then have the integral between 0 and big R of r minus r cubed over r squared, big R, which is the radius of the pipe, dr. So now this is just a polynomial that we can integrate very easily. And after integrating, we have m dot, I'm going to skip the steps and just write the final result, rho pi half r squared v max. So now that we have a mass flow rate, we may want to use this to define an average velocity, and we often do that. An average velocity in the pipe, which would be, let's call it V bar, it's m dot divided by rho times A. M dot we obtain right here. So integral of rho V dA divided by rho A is an expression for the average velocity that we can often use. For a parabolic velocity profile, you can see that if I divide by rho A, I get simply V max half. So for a parabolic velocity profile, the average velocity is 1/2 of the maximum velocity, just by plugging this guy in here. So we are going to, of course, do some more examples so that you can see how to use this in actual applications. And we'll do this a little bit later, but I want to immediately introduce conservation of momentum, so we can use them together. In general, many problems will require us to use together conservation of mass and conservation of momentum. So let's first introduce that. Conservation of momentum. Well, you remember from your basic physics the Newton's second law. Which simply states that force is equal to a change in momentum of course, when the mass is constant, it becomes our usual other form of this equation, which is force equals mass times acceleration. But if the mass were not constant, then we need to keep that and consider impulse, right? The change in momentum. So if the momentum in the fluid changes, then it must be a result of a force acting on the fluid. This is the basic idea. So if the mass in the control volume is, in general, mass is the integral of density times volume. Let's do this little extra bar on the V so that we don't confuse volume with velocity. So the momentum now is going to be the m of the control volume times velocity. So that's going to be equal to the integral in the control volume of V rho d volume. Mass times velocity is momentum. So if we have again a situation where fluid enters a pipe and we have a change of area, because of the change of area and conservation of mass that we've just seen, there will be a change of velocity. Basically, the fluid speeds up when it goes into the smaller area section of the pipe. So when that happens, there's also going to be, there's a change in velocity, and therefore there's going to be a change in momentum. Fluid enters with a momentum so fluid enters the pipe with a momentum of rho v1, and exits with rho v2. So if in the pipe, as it was shown there, we have a smaller area in the exit, A2 smaller than A1, then because of conservation of mass, we will have rho v2 is greater than rho v1. The fluid speeds up in the thinner section, right? So we have more momentum. Because there was some increase in momentum, there has to be a force applied on the fluid. The momentum of the fluid changed, and therefore there has to be a force acting on the fluid. Okay? So the momentum flux there's a flux of momentum through the surface. So if you look at time increment delta t, the momentum that enters in this delta t, the control volume, is rho a1 v1 squared times delta t. The momentum that exits the control volume is going to be rho a2 v2 squared delta t. And therefore, the net momentum flux is rho a2 v2 squared, momentum flux, so I divide over by delta t, minus rho a1 v1 squared, and that momentum flux has to be equal to the force. Now, this is for the case of this 1D approximation, basically pipe, any pipe flow where we can approximate, when we can use an average velocity, we can use this expression. Often we can do that. Often, a rocket, we can do that. We'll see that example in a moment. And but in general, we would need the integral form which is mv momentum is equal to the integral in the control volume. We've already written this rho d volume. This is if the momentum changes in both time and space, we have to use this integral form. This will all be much more clear when we do a few examples. Just bear with me a little bit more longer so that we can present the basics conservation of mass, conservation of momentum. We will use these in a couple of examples, and it will all be much more clear. Okay? Good. So I said in general we need the integral form of the momentum equation. So we had m times v is equal to, I've already written that, but let me just write it again, in the control volume, rho d volume. So I put a little bar there to not confuse volume with velocity. And so that's the momentum. But Newton's law is change of momentum equals to force. So we want to look at the change in time of the momentum, and that is going to be equal to the force. That is our Newton's law. So we want to calculate the derivative of this guy here. Now we have an integral here with two functions inside. So we, to say this rather loosely, we sort of apply a chain rule here. And I won't go through the details, but I'll just tell you that if I calculate the time derivative of this expression over here, mv, I have to consider both a time derivative. Some of you will recognize this easily. Some others will need to perhaps review. But we won't look at the details where this comes from right now. I can offer you some additional theory for those of you that are interested, video snippets later. But let's write the two expressions. One is the derivative with respect to time of this, and the other one is basically a derivative with respect to space, and that is taken with the divergence operator applied on the velocity. Now this is the most general form of the momentum equation, and it looks rather daunting. But in most cases it will simplify. The important thing here is that this equation, we can use the divergence theorem to write it in terms of a surface flux. So we take that and write now the integral in a surface, the control surface, of velocity rho and v dot the area, where the area is points outwards. It's a vector pointing outwards, or normal times dA. So this is using the divergence theorem. And what this equation tells us is that the change in momentum in the control volume is equal to the change of momentum with respect to time plus the flux of momentum, the momentum that enters the control volume and the momentum that exits the control volume. And this is equal to, of course, to the sum of forces. So sum of forces is equal to the change in time of the momentum plus the flux across the control surface Again, I said this looks a little bit daunting, but most of the times it will cancel, it will simplify much. So for example, if the flow is steady, this is equal to 0. Many times that will happen. And if there's only, say, one inlet, one outlet, then this is going to be simply the sum of m dot v for uniform velocity profile. So you see, this will become very simple for those cases. Steady, uniform velocity, many problems are like that. So You just need to know that the full equation looks a little bit more complicated like that, but we won't often have to deal with it. So that's our general momentum equation. So we see conservation of mass, conservation of momentum. The last thing that we are going to need before we introduce the Bernoulli equation, and we can do some exercises immediately, some examples immediately in the second half of the lecture, is going to be to determine what types of forces we can have. We can have pressure forces, we can have weight, or surface forces. And we just need to understand that. But let's take a small break now, a 10-minute break, and then we'll discuss the types of forces and Bernoulli equation.